And this is the same thing that we would use for reflections over the y-axis. If you take your x value that you're plugging in, let's say we want to flip something over the y-axis, and we have this x value right here. If this x value gives us this point right here, and we say that we want to look at, sorry, let me use a different color. That way we don't get confused with our first function. So this x value gives us that point, and its negative counterpart gives us this point. If we do f of negative x, it's going to take, so we plug in an x value. Let's say we plug in this x value. It now thinks that we're doing this x value because we're looking at its negative counterpart, and this x value gives us this y value. But since the x that we originally plugged in was right here, it brings that y value and flips it over the y-axis. So with this being a quadratic function, you can't really see that as well, but that's what would happen. This one's symmetric over the y-axis, so it's not going to do anything there. But if we were to shift it, as we did before, and then reflect it over the y-axis, you'd be able to see it because it wouldn't be symmetrical. So next we'll move into vertical translations, which are going to deal with our y values. So these ones are a little bit easier because our y values happen at the end of our functions. They're our outputs. F of x is the function notation, and the output that you get of from f of x, if you want to graph it, is going to be your y value. So if we wanted to vertically translate this by 2 units down, so we'll take all of our points and move them 2 units down. It'll look something like this. So building an XY table, we didn't change our X values at all, but all of our Y values were subtracted by 2. So 9 is now 7, 4 is 2, 1 is -1, 0 is -2, and so on. So our old function was f of x equals x squared. When we plugged in x, it spit out these. So we're plugging in those same x's. Those would spit out the same outputs. Like if we square these, it's going to give us these numbers. So x squared would give us these y values. So all we need to do is subtract 2 from x squared, which is f of x. So the way we write this function is f of x minus 2. It takes all of our old outputs from our original function and subtracts 2 from them. So vertical translations are a little bit easier than horizontal translations, less complex. So we can apply that same reasoning to vertical stretches and compressions. If we wanted to take this graph and stretch it out vertically by 2, so we're going to multiply all of our y values by 2. That y value is 4, so now it's going to be 8. Here we have 9, so it's going to be way up here. So this graph is going to look something like this. So just like before, all we did was we took our y values And instead of adding or subtracting to them, we multiplied them this time. So 9 is now 18. We have 8, 2, 0, 2, 8, and 18. But we didn't change any of our x values. My bad, I got ahead of myself. So there's our XY table for this. And all we did here was we took our Y values and multiplied them by 2. So our Y values are equivalent to our f of x, which is equivalent to x squared. So all we have to do to write this algebraically is take 2 times our old f of x values. F of x, when you plug in -3, gives us 9. And then if we take 9 times 2, it'll give us that 18. So it'll stretch or compress. If you multiply it by something that's less than 1, it'll get smaller vertically, your original graph. And just like before, this is the same reasoning we use for reflections, but this time over the x-axis. If we wanted to take our original graph and reflect it over the x-axis, so it might look something like this. It's the same graph, just now all of our y values are negative. So that would be the same graph, and our f of x values are our outputs that we get from running x through our function. So if we just make our y values negative, that is what's going to give us this new graph that's reflected over the x-axis. So overall, we have really two different lines of reasoning. Here we have horizontal transformations where we have to almost trick the function into thinking that we're plugging in what we already know from our parent function, but we're actually plugging in what we want it to be. That way we can shift our function to the left or the right, or we multiply. That way we can stretch or compress our function by making it think that we're plugging in what we already know, but really we're plugging in what we want it to be. That way it takes those y values and stretches them out or compresses them. And here we have our y values, which are just the outputs of our function, so f of x. So all you have to do is take f of x and subtract or add to it to shift your graph up or down. Or if you want to stretch it or compress it vertically or reflect it, all you have to do is multiply your f of x or make your f of x negative. So the reasoning behind why there's those two different lines of reasoning is because when we deal with x's and things that are horizontal, we have to get to them before they go in the function. If you notice, here we do our x plus 3 in these parentheses. So we add 3 to whatever we're plugging in before we run it through the function. And then that gives us the right output. But down here, when we're dealing with it vertically, f of x is the output of the function. So x has already gone through, and f of x is equivalent to our y when we look at it in a graphing sense. So if we want to change our y, all we have to do is take it and multiply it by 2, or add or subtract 2, or do whatever we need to do to get it to move up or down, or stretch or compress up or down. And that is horizontal and vertical transformations. Your stretches, compressions, translations, and reflections. Hope you enjoyed.